And now I want to focus on a slightly different idea. So let's go back to this sample, and let's ignore the fact that respondents are not exactly equal to a sample. Let's just say, this is a set of people who I'm going to try to include in my study, and I think they're all going to do it. Okay. Suppose that my study is an experiment where I'm trying to learn about the effect of one treatment versus another treatment, right? So I'm a psychologist. I have the people who are going to participate in my study, and now I need to decide who is going to watch a video before they answer a bunch of questions, and who is going to be locked alone in a room for a while before they answer a bunch of questions. I don't know. Maybe I'm interested in the effect of the video versus being locked alone in a room. I don't know of a study like that, but I made it up. There you go. Okay. So we have a bunch of people, right, in this sample. How do we decide how to divide them into two groups? Now, I believe I've used all my colors on this Zoom iPad, so I'm going back to blue. Okay, so suppose I'm trying to divide them into two groups here. Okay. Turns out there's a parallel between assigning units to groups and sampling from a population. So once I have this set of people who are in my sample, how do I divide them into two groups? Well, I could do it haphazardly and just say, oh, everybody choose whatever you want, right? Choose whether to watch a video or go alone in a room. Or I could do it by simple random sampling. I could put all the people in my study in a hat and randomly draw some of them to watch a video and block the rest alone in a room, right? Or I could do it by stratified sampling. I could say, okay, like now that I know who's in my study, let me group them by major and choose a couple people from each major to watch a video and the others from each major to be locked alone in a room. Or I could do cluster sampling. Now that I know who's in my study, by major, let me choose a few majors to watch videos and the other majors will be locked alone in a room. I could do it by systematic sampling. Every seventh person who's actually in my study could end up watching a video. The rest are locked alone in a room. I should have chosen a different example, but we're going with it, guys. Or suppose that we have Bernoulli sampling. Every time somebody's actually in my study, I'm going to flip a coin to determine whether they're going to be watching a video or locked alone in a room. So those are all things that I might do once I actually have a sample to go forward with the next step in my study, to decide which group they're going to be in. And there's a parallel there. And that parallel actually means that the mathematical theories that are derived about sampling units from a population are the same mathematical theories that we use when we're learning about assigning units to groups. So assigning units who are actually in your sample to groups. Okay, so I'm going to say that this parallels sampling from a population, because the goal is to create groups that are representative of each other, right? So just like I want my data set to be representative of my target population, once I actually know who's in my study, I want the people who watch the video to be representative in terms of baseline characteristics of the people locked alone in a room, so that I can compare their final results and attribute that to the treatment that I assigned. So it could be haphazard or any of the random strategies that we discussed. Any of the strategies we listed. It's very common for it not to be random. So if you do end up with two representative groups within your sample, then what you can draw is causal inferences. You are allowed to say, okay, I think the difference in final survey outcomes is because some of these people were watching a video and some were locked alone in a room. And I can do that because I believe I've created two groups that are similar to each other, representative of each other on baseline characteristics. So although in this course, this is just one slide here, this actually is my own research field, causal inference. How do you show that something causes something else? What ways can we think of to create two groups that are similar to each other at baseline? And how can we use that to learn about causation, not just correlation? And I teach a whole course about that. And once you finish this summer course or Stat 260, you could take Stat 309 and learn about those ideas. I'm going to draw a picture now to summarize what we've talked about. So first we talked about sampling units from a population. I'm going to make a little table here, but let's point out that we said that that could be using a random strategy or not. Now, I sometimes use a textbook for this course called The Statistical Sleuth. Sometimes I don't. That textbook has a table that is similar to the table I'm drawing here, although I am changing it a little bit. Because the book says, let's draw this table. The book says that if you randomly sample from a population, then that means that your results will be generalizable. And I agree with that. That is true. Generalizable. Let's try to make that word more legible. Let's write it again. Generalizable. So if my sample population is similar to my target population, if my sample is randomly selected for my sample population and that I don't have any kind of response bias, then I have generalizable results. In other words, the people who actually responded, who actually participated in my study, where I'm trying to see what Wellesley students think about remote learning, will have views that are representative of the views of all Wellesley students. Or the people who actually reported their household incomes will be representative of all US households. So that would be good, right? If I'm trying to learn about some estimand, it would be nice if my sample, my final sample, is representative of the target population, so that when I use my sample to estimate the estimand, I get something that is hopefully close to the right answer. So that is totally true. What the Statistical Sleuth textbook says that I don't love is that if you do not randomly sample from the population, then your results will not be generalizable. In other words, what the book says is if you do not use a random method to decide which Wellesley students to talk to, then you cannot, no matter what, say that those results are representative or generalizable, can be generalized to all Wellesley students. And I think that's too harsh. I think what we should say instead is that it's harder to generalize. Okay, it is harder to generalize. But if I do collect some data on Wellesley students in a way that is not random, if I observe the characteristics of those Wellesley students, like I ask them about their majors and their backgrounds and maybe their dorms or demographics, whatever it is that might be relevant to the question, there are ways to take that sample that was not chosen randomly and still use it to generalize to the target population that I was interested in, right? So just to give you a little sense of how that might work, suppose that I happen to choose too many math majors in my sample that was not random. Well, in the end, I could just put a little bit less weight on the math majors when I'm trying to generalize to the target population, right? Because I know that math majors, like suppose math majors are half my sample, I know they're not actually half of all Wellesley students, so I could use my math majors in my sample to make a best guess at the views on remote learning among all math majors, and use the rest of my sample to make a guess at the views on remote learning among all non-math majors. So if you sample from a population randomly, you get generalizable results. If you sample from a population not randomly, it is much harder to generalize. Then we have this idea that once you have a sample, you might be assigning groups. Now, plenty of studies don't involve comparing two groups. Like if you're only trying to learn about the average household income in the US or the average view on remote learning among Wellesley students, you don't have two groups. But if you're doing a psychology study where you are trying to learn about the effect of one treatment versus another, now you have two groups. Or if you're doing an econ study where you're trying to learn about the effect of going to college versus not going to college on your income, now you have two groups. So groups also can be assigned randomly or not. And if you assign groups randomly, then you should be able to infer causation, right? So I have my sample of Wellesley students who are going to be in my psychology study. I randomly assign some to treatment A, some to treatment B. I should be able to say at the end that treatment A versus treatment B causes any differences I see at the end. Here's the other place where I disagree with the textbook. If I do not assign my groups randomly, then the textbook would say, therefore, you just cannot infer causation. There's no way to do it. Right? So if I'm looking at people who went to college versus people who did not go to college, and I'm looking at the impact of college on their incomes, according to that textbook chart, I should never be able to say, oh, that happened, that income differential happened because they went to college. I think that's too harsh. Again, that's my research area, so I know it's too harsh. It's just harder to infer causation if you don't randomize, but it can be done with a lot of caution. So let's think about what kind of studies actually fit into these boxes that we have here. So a study that has random sampling of units and random assignment of groups is very rare. In fact, I don't think I've ever heard of one, like a real one, not one that's not a little toy example in statistics class. It's also ideal. That's what we always assume we're doing when we use statistical methods, that we randomly assign groups within a sample that was randomly selected, right? That's what we always assume, but it's not true. Okay, that basically never happens. What about these other boxes? Well, if I randomly sample units from a population, okay, so I randomly sample units from a population, then I'm in this top row here, but then suppose I assign groups in a way that's not random. So I'm in this box right now, and that's an example like I randomly sample in a representative way people across the US, and then I just ask them whether they went to college or not. So now the people in my study are representative of all Americans, but within that sample, the ones who went to college are not representative of the ones who didn't go to college, right? I didn't randomly assign people to go to college or not. So my results will be generalizable, and that I can say, things like, oh, the proportion of people who went to college in my sample is probably similar to the proportion of people who went to college in the whole US. But I won't be able to infer causation. I won't be able to say that, oh, these people have higher incomes because they went to college, because there are probably things about the kind of person who went to college that are different than the kind of person who did not go to college. So this is common among survey analyses. If you are using government data or government surveys or pre-existing surveys to ask a question, sometimes this is done in econ or sociology, right? If you're looking back at who went to college versus not, you're probably in this box. You might have a national survey that was designed to be generalizable, but if you choose which groups to compare, it's going to be harder to infer causation because those groups were probably not randomly assigned. What about this box? Well, here we have cases where the sample is not randomly chosen from the population. So I'm doing a psychology study, and whoever walks in to be paid $10 for half an hour of their time is going to be in my sample, right? Whoever responds to my email like, hey, I really could use some people to participate in my study, that's my sample. Are the people who participate in Wellesley College psychology studies representative of all human beings? Definitely not, right? And that's actually a problem the psychology community has grappled with in general, right? What about the fact that so many psychology studies are conducted on college students, because that's where psychology researchers are, right? That's an issue that people have thought about and tried to deal with. So then again, the sample is not representative of the population, so it is harder to generalize, right? It's harder to say, oh, this result I found on my Wellesley students is going to tell me about all human beings ever in the world, but the groups might be assigned randomly. So I do get to say that there's causation. So this is often true for lab experiments. So I'll be allowed to say, hey, among my Wellesley students, treatment A versus treatment B caused this difference in results, but I'm not sure whether that result would generalize to all human beings, right? Well, this applies to experiments on like rats too, or mice, right? If I randomly assign which mice get treatment A versus treatment B in my study, I can say, hey, I think that these treatments seem to cause any difference in outcomes that I observe, but are the mice in my study representative of all mice? Well, that's something I need to figure out. Maybe they are, but maybe not, right? Maybe not. What about this box? This is where most studies are. Most studies you read about in the news are neither consisting of units that were randomly sampled from the population, nor based on assigning groups, right? Neither one. So most of the time, somebody posted a link somewhere on the internet, said, hey, participate in my study if you want. And then once they collected that data, they compared the people who went to college to the people who didn't go to college, right? So it is going to be hard to generalize those results to any particular population, and it's going to be hard to infer causation. One note that I'll give you before I stop here is just to say that you don't always figure out what the target population is beforehand, especially if you're analyzing someone else's data. So it may be the case that once you figure out, who's actually in the study, you say, okay, like I wish I could have generalized to all human beings. This study is not generalizable to all human beings, but it is generalizable to all Wellesley students. Maybe I believe that. So then I say, okay, well, if my target population is Wellesley students, then this is a generalizable study, and you just constrain your study in that way. So all studies you look at should fit into one of these four boxes. If the studies are not comparing two groups, you might just be thinking about whether they're in the top row or the bottom row. But this is what you need to be thinking about. Anytime we talk about a study, even if we're doing some complicated model on it, even if we're doing some complicated data science technique, once you have that result, once you come up with results that are actually numbers, your job is always to sit down and make sure you can clearly explain written words, orally, is this generalizable? If so, to what population? can I learn about causation? Because otherwise, I'd better be really clear about the words that I choose as I describe my results.